here is week 3 notes, and it covers just one topic, so limiting reagent. So if you want extra practice, that is something that you need, that you can look up, limiting reagent problems. Keep in mind, in most of those problems, they're going to ask you to balance the equation first. And I will give you a balance equation, and we'll do balance equations next. Reactants form products. Excess reagent is what is left over in a chemical reaction. So you can never mix two things perfectly. So, I mean, I guess you could, but at a molecular level, something's going to run out before the other. Limiting reagent is the thing that runs out. Expected yield is what you should get. Percent yield is actual divided by theoretical times 100. So essentially, again, I always think free throws. I make 3 out of 4 times 100, and that's 75%. So like what I made over theoretical. So like, I mean, any coach would say, oh, you got to make all your free throws. That's why they're called free throws. You know, I heard that stupid saying my entire life. But, you know, you're not going to make all of them. So you don't need to know the wording of this, especially NH3, but keep in mind N2 nitrogen is a diatomic, like H2 is a diatomic. So if we say hydrogen and nitrogen react to form NH3, and you're not going to have to balance those reactions. That's what this is. Now, I'm going to write something that might help you solve these. Grams to moles to mole ratio to grams. So this is something that I've taught more than, I don't know, just about anything, because it shows up on a lot of, really on all, you know, a lot of standardized tests. So students seem to like this more than my sandwich thing. 2 pieces of bread plus 1 piece of cheese forms a sandwich. Grams to mole ratio to grams, and we'll do examples here. All right, so we have 14.6 nitrogen, blah, 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 blah. So let's just write that reaction out. So I'm just going to write the reaction. I'm going to say out loud, but this is not something that you're going to have to do on Unit 1 test, but it's good to hear. Nitrogen, 1 mole of nitrogen, there's nothing written in front of that, plus 3 moles of hydrogen, diatomic, forms 2 moles of ammonia, NH3. And we have to determine what is the limiting reagent. And so we have 14.64 grams of nitrogen and 16.3 grams of hydrogen. So something has to run out again. Something has to run out first. You know, it's not as simple as buying the same amount of hot dog buns as hot dogs, because we're in chemistry working with such small quantities. So we have to find out what runs out first. And I'm just going to write grams to moles to mole ratio. No, I'm not going to do that yet, sorry. So we got to find out what runs out first, because that's the thing that determines, you know, if you do bring 5 hot dog buns and 3 hot dogs, you know, it's a 1-to-1 ratio. So, you know, how many people can eat hot dogs? And it's just 3. So that seems easy, but it never really, that analogy never really goes over great, or it doesn't translate well. So anyways, we have 14.64 grams of nitrogen. Grams, we have to go to moles when we go from grams to moles. And remember, whenever you have grams, you have to convert it to moles. So grams to moles, 1 mole of nitrogen is 28.02. If you look at the bottom of nitrogen on the periodic table, nitrogen is 14.01 times 2 is 28.02. And so grams to moles So now we have moles, and essentially we could say that per reaction there is one nitrogen reacting. Or you can convert it to moles and divide it by the front number, which I think translates better. So here, 14.64, so multiply across like this. So we have 14.64 divided by 28.02. That is 0.225, 5225, sorry, moles of nitrogen, and I'm going to divide it by the front number. So that's just saying per one reaction, one nitrogen is used. Just like if we have two pieces of bread and one piece of cheese, per reaction or formation of a sandwich, two pieces of bread are used. So that ends up being 0.5225. And we have to find the lowest of the two numbers to determine limiting reagent. So you are given two things, nitrogen plus hydrogen forms ammonia, or 1 mole of nitrogen plus 3 moles of hydrogen forms 2 moles of ammonia. So now we have to take the grams of ammonia, or of hydrogen, and determine if that's a limiting reagent. So we have 16.3 grams of hydrogen. We have to convert it to moles. So grams to moles for later, grams to moles to mole ratio to grams. Now it's just like grams to moles divided by its front number, essentially, and that's a way to determine limiting reagent. That seems generic, or it seems, superficial and not necessarily thought-provoking. But if I told you, if I give you bread and cheese, it'll be exactly how you would solve it, and you'll be able to solve it in your head in seconds of which one will run out first. That's exactly what you're doing. So grams of hydrogen, we know 1 mole of hydrogen is 2.02 because the bottom number for element 1, hydrogen, is 1.01. If you use 1.008, that's fine. That's what Alex will want you to do. But here, 16.3 grams divided by, so that is 8.07 moles. And we're dividing it by the front number because we use 3 moles of hydrogen for every one reaction. So I'm going to divide that by 3, and I'm going to get 2.69 essentially reactions, or 2.69 NH3s can form. So we take the lower of the two, and that is a limiting reagent. So here it was 2.69 can form. For the nitrogen, it was 0.5225 can form. So this is the limiting reagent. It's what runs out first. So we don't even care about hydrogen anymore, other than, it's going to be asked what is the excess reagent. And so hydrogen is excess reagent. So if you go to a cookout and somebody brings a whole bunch of buns and somebody brings just a couple cheeseburgers, like the patties, you don't care about how many buns you have. Like, all you care about is the patties. That's the only thing that's going to feed you. And so that's how because the buns are the excess reagent. So let's determine the percent yield. We know that nitrogen is the limiting reagent. And remember, grams to moles to mole ratio to grams. We want to find how much is being made. We have grams of an N2. 1 mole of N2 is 28.02 grams. So I'm repeating the steps from before. So it doesn't matter if you do or not, but we would already have the answer to this. Anyways, grams to moles, we now can cancel out grams and we have moles. Now we have to do mole ratio. So the reaction is nitrogen plus 3 moles of hydrogen forms 2 moles of ammonia. So we want to know how much ammonia we can make. Moles of what we want, 2 NH3s, over the mole ratio of what we have, which is 1. And those cancel out, or even if it doesn't cancel out, just remember grams to moles to mole ratio to grams. Mole ratio is what you want, or the product, over what you have. Now we have to figure out how many grams this is. When you go from moles, so if we canceled everything out, we have moles here. Now if you want to go from moles to grams, grams to moles to mole ratio to grams. To go from moles to grams, you multiply by molar mass. NH3, nitrogen is 14.01, hydrogen is 1.01, so therefore NH3 is going to be 17.04 grams. Multiply these across like that and essentially divide them, and you are going to get 17.8 grams of NH3. So grams to moles to mole ratio to grams. To go from grams to moles, you divide by molar mass. So when I work with students, I often ask, how do you go from grams to moles? You know, you're going to be in this class long enough where you almost subconsciously have to say you divide by molar mass. How do you go from grams to, or moles to grams, you multiply by molar mass? And, you know, it's just what it is, because this is something that will be more cumulative than other things. And then if you take Chem2, I mean, it's just like nonstop. You know, a freaking mole is like freaking everything. Anyways, so now we have the expected yield, meaning if someone gave you that many grams of nitrogen and essentially, to the best of your knowledge, excess hydrogen, because it's the excess reagent, that's what you should produce. So we have to find percent yield. So remember, it's what you actually got, which it says 14 grams, over expected, 17.8. And I'll make sure it's less than 100%. For the next one, it ends up being like 200% yield. Like, that's not really possible unless if there's something that went wrong, or not something went wrong. Like, when I say something went wrong, something went really wrong, and it's not actually what you think it is. So like, you can't make more nitrogen and hydrogen. So anyways, here, if we divide those, so 14, what we make, and then what we should make, we get 0.79, and that's because of 2 sig figs, 1, 2, 1, 2 times 100, and we get 79%. So it's 79% yield. So we have to determine what the limiting reagent is. That's what matters. Go grams to moles to mole ratio to grams. Divide what was actually found, or actual, divided by theoretical, or whatever helps you remember it, times 100. So this is something that you're going to learn very soon, and it's combustion, where oxygen reacts with a carbon-based compound to form CO2 and H2O. But whatever, forget that. It doesn't matter now. We have a certain amount of CH4, which is methane. Again, that doesn't matter now. And 23.4 grams of oxygen. The only thing that really matters there is we know oxygen is O2 because oxygen is a diatomic. So let's solve all this stuff here. So again, the reaction is methane reacts, or 1 mole of methane reacts with 2 moles of oxygen to form 1 mole of carbon dioxide plus 2 moles of water. So this is a balanced equation, but don't worry about that. You'll be given a balanced equation. We have 22.4 grams of CH4 and 23.4 grams of O2. We have to determine limiting reagent because, again, at the picnic, you only care about what's running out first. So we need to solve for methane first, or CH4. We have given how many grams it has. So we have that much grams. The molar mass of CH4 is 16.05 because the bottom number for carbon, if you look at your periodic table, element 6 is 12.01. Hydrogen, it is 1.01. If you have 4 hydrogen and 1 carbon, you know, each hydrogen is 1.01, so that's 4.04. 4.04 plus 12.01 is 1 mole. To go from grams to moles, you divide by molar mass. 1 mole is 16.05 grams. We're going to solve that, and in the notes that I took, I did not record the right molar mass. So 22.4 divided by 16.05, yeah, 22.4. So well, we had 3 sig figs, 4 sig figs. That is 1.40 moles of O2. I'm going to divide it by the coefficient, 1. And so essentially we have 1.40 reactions that are taking place. So writing units is always important, but this unit reactions is sort of generic. So I wouldn't take off for not having that unit. We know we have 1.04 reactions for methane. So now let's solve it for oxygen. Again, 1 mole of methane, 1 mole methane, or 1 mole CH4 reacts with 2 moles of oxygen to form carbon dioxide and 2 waters. And now we have 23.4 grams of oxygen. So whenever you have grams, if you look at that molar map, when you have grams, you can't go anywhere else other than to moles. Like there's no arrow pointing in the opposite direction. So we have 23.4 grams of O2. The bottom number on O2 is 16.00. So O2 is 32.00 grams. We're going to solve for that. And then we're going to divide it by the coefficient. So 23.4 divided by 32, 0.731. We can divide that by 2 because there's a 2 here, meaning every single, let's say CO2 is a sandwich, every single sandwich made, we use 2 oxygens. Hence, it's used up twice as fast. So we're going to divide that by 2, and I get 0.366 reactions. So this ends up being the limiting reagent, the one that runs out first, or the one that has a lower number at this point. So we can forget about, or well, you can label CH4 as excess reagent. And the only thing we care about is the 23.4 grams of oxygen. So now we have to find the percent yield using the only thing that matters, which is oxygen. I'm just going to write the reaction again. Methane plus 2 moles of oxygen forms carbon dioxide, 1 mole of carbon dioxide, and 2 moles of water. The only thing we care about is oxygen, which has 23.4 grams. And we want to know how much carbon dioxide should form. So we have 23.4 grams of oxygen. Whenever you have grams, you divide by molar mass. So again, what would stick and is grams to moles to mole ratio to grams. Mole ratio is the scariest thing in that, but it's just the front number of what you want over what you have, and it's just okay. So we have grams. Whenever we have grams, we have to divide by molar mass. So 1 mole of O2 weighs the bottom number on oxygen. So we're doing the same step that we did in the last slide, is 32.00 grams, and you don't have to resolve it. Grams to moles. Now mole ratio of what we want, 1 carbon dioxide forms for every 2 oxygens. And then how much carbon dioxide is formed? Should we form 44, so grams to moles to molar mass, or grams to moles to mole ratio to grams. Carbon dioxide, since oxygen is 16, there's 2 of them, that's 32.00, plus carbon is 12.01, so that's 44.01 grams per 1 mole. So if you're good with units, then we can cancel all that out, and we then see that essentially we have grams of carbon dioxide. Now, when I was your age, I would see something like this, and I would say, I can figure this out rationally and do it rationally. And I don't know how successful I was, but I know that it was a bigger headache, just figuring out rationally. But it can be done. I mean, it undoubtedly, you look at this long enough, you sort of see, well, this is, rationally speaking, makes sense. And the amount of CO2 that we should get is, so again, multiply, dang it, I don't think it lets me undo. Well, anyways, multiply across, so go back, like, it doesn't let me undo that when I'm videotaping. Multiply across and then divide down, and we should get 16.1 grams of CO2. So now, remember, percent yield is what you actually got, or free throws you made, over what you should got, free throws shot, divided times 100. Now, when I wrote this worksheet, I just was like, whatever, I can write whatever, it'll make sense. But I wrote like big numbers. So it says on that slide, or at the notes, it says 34.3 grams of CO2 is actually formed, and we should form 16.1 grams. Now, again, this would be impossible because that's saying that we are creating more carbon, more oxygen. So in the laboratory, a student said, and I should have acknowledged him or her, I think it was him, that means that the product is probably wet. And that's actually 100% true, because that is when you get results like this, because you didn't dry out the product. I mean, that essentially is like the case almost all the time, meaning there's water still in there, and that's what's causing the heavy mass. And so, anyways, let's solve it anyways. And 34.3 divided by 16.1, and we get 2.13, 3 sig figs, times 100. So then, 2.13, yeah. So then multiply by 100, and that's 213%. So our percent yield is 213. Again, when I give you one in the test, I will solve it before I just write numbers. And because generally speaking, you're not going to have, but I guess maybe this is good because it also shows you whatever. Okay. This is the Alex that is due, and not too tough. I might as well put one on the test because it shows you how to identify limiting reagent in a visual sense. And again, this is something that you would see on a lot of standardized tests. So if you took AP Chem, I mean, this is like straight out AP Chem question. So let's rationalize it though. We have this reaction below. We have CH4, which is methane, and we have O2, oxygen, diatomic. And we want to know what is the limiting reagent. So if one methane reacts with 2 oxygen, it's just like the sandwich thing. So methane, we got 4, and oxygen, we got 1, 2, 3, 4, 5, 6. We know that it's like giving someone 4 pieces of cheese and 6 pieces of bread, that the oxygen is going to run out first, or I'm sorry, the bread's going to run out first. It is the same thing. I don't know. I got to find a better way to verbalize it because it doesn't, that analogy doesn't usually work. But anyways, you take how many there are. We have 4 methane, and we divide it by the coefficient, 1. So essentially, you can make 4 product from that. Oxygen, we got 6 oxygen divided by the coefficient, and we get 3. Therefore, oxygen is the limiting reagent. So in a quicker sense, let's just find the NH3s. So that is ammonia. We got 1, 2, 3, 4, 5, 6. 6 divided by coefficient, that's 1.5. Oxygen, 1, 2, 3, 4, 5. You have 5 oxygen divided by the coefficient, that's 1. The lower the two numbers is the limiting reagent. So this is the only other Alex do. I don't think I'm going to put this on the test, but it introduces you to balancing equations. What's the total? So this is a balance equation. It goes, what is the total number of oxygen atoms on the right-hand side of the chemical reaction? So the right-hand side is the product. So you got to count the oxygens. We have KHCr2CO10. That 10 gets distributed in. So we could count 10 oxygens there. Plus C2CO3. We got 3 oxygens there. Plus KHCOO. So there's 2 oxygens. So a student's going to think, okay, well, that's usually written O2. But get used to that COO, not really for this class, but for cell biology or physiology. I mean, that COO comes up. Not really in this class, but then we have 2 there. But O2 is the same as COO. And then H2O. We have 1 oxygen. And so here, oxygen is only diatomic if it's alone. So oxygen alone is O2, but that does not mean that if it's bonded with something else, it has to be a 2. So water is an example where I'm trying to think of an analogy. I have a good analogy in my head, but I don't want to do it like, I don't know if it's going to go well. So I don't want to put it on YouTube the first time I tried it. So whatever, I'll think about it, maybe try it later. So anyways, oxygen, when bonded, does not have to be O2. So here, total amount of oxygens is 16. Yeah, okay, on the product. We got another one of these. So on the right-hand side, chemical reaction, C6H12O6, we have 6 oxygen, that's glucose. You don't have to know that that's glucose. Oxygen, 6O2, that's 12 oxygens, we got 18. So I think the big thing is for you to review is the limiting reagent and excess reagent. And grams to moles to mole ratio to grams. So it takes some practice, but it's the same process over and over again. And that is it.